Thank you and welcome everyone. It's my great pleasure to welcome you to topic 4 of our breakout sessions for today. My name is Victoria Coleman. I'm the Section Manager of Nanometrology at the National Measurement Institute of Australia, and I'm also the APMP Lead Technical Committee Chair. I will be your chair for this session, and I'm here with my moderator, Stuart Chalk from the University of North Florida, and Stuart is also on the steering committee for these meetings. So Stuart, do you want to say a few words about how you will manage the questions today?
Absolutely, Victoria. So if you have questions as we go through this session, please put them into the chat at the top right, and I will be looking at all the questions that come in and then promoting the ones that I think our experts can answer. And then once those are available to you guys, go ahead and click on the thumbs up button with each message to promote it to the top of the list. And then we'll go through the priority questions when we get to the Q&A session.
Great, thanks, Stuart. So the way today runs, we have actually 2 different rounds, and so you're currently joined into session 4 for the first round, and our topic is readiness of data for artificial intelligence and machine learning. So we have about 45 minutes for this round. We've got 2 presentations. After that, there'll be a short break when you can change sessions, and then we'll basically repeat the sessions over again. And then we'll finish up for the day. So in our great session coming up, we've got 2 talks from 2 speakers who are also both with us live today for the panel discussion. The first speaker is Alistair Forbes, who is a fellow in data science department at the NPL in the UK. And the second speaker is Professor Dr. Marcus Barr, who is the head of the Department of Mathematical Modelling and Data Analysis at PTB in Berlin. So really looking forward to these presentations, which we'll go through now. They're pre-recorded, and then after that we'll join you with both the speakers live for hopefully some really stimulating open discussion. Thanks.
Hello, I am Alistair Forbes, a mathematician working in the Data Science Department at the National Physical Laboratory, the UK's National Metrology Institute. I want to say a few words about this discussion session in the context of the SI Digital Framework Initiative. The SI provides a basis for the international measurement system. The aim of the SI Digital Framework is that all aspects of this measurement system, measurement results, uncertainties, traceability, calibration, and so on, can be accessed and interpreted digitally, enabling machine-to-machine communication, enabling the analysis of data by computer systems, for example, statistical analysis, finite element analysis, computational physics and computational chemistry calculations, and also the analysis by artificial intelligence and machine learning systems. The framework envisages 3 layers: the core layer, a service layer, and an applications layer. The SI core layer is concerned with the basic elements of measurement, representing measurement results in terms of a numerical value, associated unit, and uncertainty. The service layer is concerned with the wider services and products provided by the National Metrology Institutes and similar organizations that directly support the integrity and traceability of the measurement system. The applications layer is concerned with tools and services developed and deployed in the broader scientific and technical community, and includes analysis and artificial intelligence and machine learning methods. This discussion session primarily relates to the applications layer. The FAIR principles feature strongly in this workshop. These principles are aimed at improving the findability, accessibility, and reuse of data, particularly by computer systems operating with little or no human intervention. The FAIR principles are there to help machines perform tasks that are useful for us. While the immediate aim of the SI digital framework is to provide machine-readable data, this longer-term aim is to provide machine-actionable data. The data should enable interpretation, analysis, reasoning, and decision-making by computer systems, again, operating without human intervention. For this to happen, the computer systems must, in some sense, understand the meaning of the data. So the correct interpretation of data will generally require an appropriate knowledge, representation, and reasoning framework, employing controlled vocabularies, taxonomies, ontologies, and the like, and inference tools based on logic and statistical inference, for example. There are many issues that you may want to discuss in this session. One topic of interest is how can we ingest data and metadata into analysis systems? So we want to make sure that technical data is represented correctly. But we must also be concerned with the FAIR principles. In particular, the data must specify what individual or system it relates to, what physical artifact, what individual, which chemical compound material, and so on. And this is really what findability in FAIR is about. A second topic is how we assure and assess the trustworthiness of the outputs of analysis systems. A fundamental aim of metrology is to ensure that measurement data used in analysis is trustworthy. But we're also concerned with the trustworthiness of the outputs, not just the input data. And this presents a particular challenge when the outputs depend on training data, depends on models, depends on algorithms and software. So a related topic is how can we encode the provenance of models and algorithms and software in workflows? We may be able to specify the provenance of the data, but how do we specify or encode the provenance of the model, algorithm, and software underlying the analysis? I hope you enjoy the discussion session. I now pass you back to the chair of the session.
I will talk about the potential role of reference data for trustworthy machine learning and artificial intelligence algorithms, taking a metrological viewpoint. In the first part of the talk, the relation between machine learning and metrology is discussed, and in the second part, I will present a use case stemming from a European project in a medical physics application, and finally, I hope that this will give some ideas what could be potential passes towards standardization. For the role of machine learning and metrology, I can cite results from an artificial intelligence survey conducted among 14 European NMIs in the framework of the European network MUSMET, which is a part of Euramet. And here this relation was considered from two different angles. So one viewpoint was, are there things metrology can contribute to artificial intelligence? Can it improve these methods? And the other direction was, in what sense do these new algorithms are extending the capabilities of metrology? And on the first item, obviously, classical quality infrastructure aspects such as uncertainty, traceability were mentioned. Robustness, explainability are other things which you would like to have for a solid metrological assessment of artificial intelligence results. On the other hand, of course, there's many computationally intensive metrology applications where artificial intelligence algorithms may be beneficial or enabling. I listed some typical tasks which are often difficult to solve, and in particular here new applications of distributed measurement systems such as sensor networks or in general systems which produce a lot of data are potential beneficiaries. Okay, so from the results of the survey, there were less answers for the potential of AI for metrology, but certainly handling of big data is in the bigger NMIs an issue. Again, sensor networks, distributed systems feature highly, and it was also sometimes said that systems metrology is an emerging field. So there will be more and more systems where large number of measurements are combined. Another area, of course, highly resolved imaging and microscopic processes where a lot of pixels are produced. More answers came in the direction of how metrology can support for artificial intelligence. A potential connection was in particular seen in transferring ideas on uncertainty and traceability. And there, obviously, one main issue is how the input of measurement uncertainties affects the outcome of artificial algorithms and what procedures enable this determination. And the second most cited application there was reference databases, and that's actually the topic of my talk. And that could be measurements, but I will also have an example in a minute on simulation data. The general issue is, of course, data quality is a possible basic way to assess the suitability of a reference database. And all of this feeds into standardization, obviously. For future research priorities, consequently, trustworthiness, security, and contributing to quality infrastructure was mostly cited. The training data quality featured high in the column on the reliability, which in general seemed to be the most important concern for metrology institutes. I will not say much on explainability today, but certainly traceability with the uncertainty issue is a main concern, and examples in metrology should be identified and are important to put this area forward. So I will give you an example which comes from a project in the European Metrology research program, EMPIA, and that is metrology for electrocardiographic automated data analysis. It's running a project called MedalCare. We reached halftime now, and the two main objectives is, first of all, to assess metrology for advanced data analysis, including machine learning. And the second part is to provide reference data for these artificial intelligence, actually to enable such benchmarks. And here we started from a clinical ECG database, which is called PDB-XL. And the goal of the project is nevertheless to extend that and to provide a data base made out of synthetic data with a ground truth. And that means they will be generated by established biophysical models. And there you know exactly what you put into the simulation, what kind of pathology is implemented in the model, and how it affects the ECGs. And obviously, hopefully, if this all is successful, it will further clinical applications and standardization in this important practical point. So a reference database of measured clinical reference data is PDB-XL. It has 20,000 ECG recordings of 10 seconds duration, and in each of these records are 12 leads measured. And for each of the recordings, we have a diagnostic and rhythm statement from two experienced cardiologists who use the well-known ISO standard classification, and that leads to separation of the whole database in superclasses. So about half of the ECGs were from healthy, normal people. Then there's different pathologies, and each of these pathologies goes again into subclasses. This was done in collaboration with the Fraunhofer Heinrich Hertz Institute and is published in Scientific Data. Now, with this database being available, well, there was a first benchmark carried out for different types of machine learning algorithms and also some conventional signal processing algorithms such as wavelets. You can see the results. In general, it was found that machine learning is superior with high success rate at above 90% compared to all conventional previously used algorithms, especially ones who extract features, which is often what software in the practical doctor's practice will do. And then also first steps were done towards explainability. As I said, this is not the main feature, but you can use this information also to identify the parts of a 12-lead ECG record which have most influenced the classification in one particular illness class. Again, this is also just published by our Fraunhofer colleagues in collaboration with PTB. But the main point of the project was its new aspect, implementing a modeling pipeline. And here that requires modeling of the ventricles and the atria of the heart. Here the ventricle part is shown. So you define mathematical equations and you run them. And first it's done on the isolated surface of the heart where you can make catheter measurements and validate these models so that all has been worked out already. And then in a second step, to get the ECGs, you have to embed them into torsos. And here we have a cohort of 13 models taken from direct medical imaging recordings, different hearts embedded in different torsos, obviously, and the black dots in each of the pictures are the points where the ECGs are taken. Okay. And if all of this is put together, you can simulate ECGs for each of these people. You can also put pathologies in the cardiac dynamics, which are often mechanistically known, and then you get the resulting ECG here plotted in a typical version that doctors are familiar with. And you can also superpose noise. So in other words, you can vary the quality of the data and then see how that may affect the machine learning algorithm. The main goal is actually to test such algorithms with well-defined data records. Okay, and that brings me already to the summary. In short, I discussed a bit the issues that metrologists found important in trustworthy machine learning. Main conclusion is, of course, training data are key. And in particular, we have a lack of quite high quality references. So we should work to set up reference databases and also find criteria to assess these databases. And that would be measurement data. But another second path, which is very promising, is to use synthetic reference from digital twins. The medical example I showed is already very complex with respect to the processes and equation set up, but obviously this can be beneficial probably in simpler, better understood physical processes. And hopefully if these things can be established, they can be an important element in the standardization rules for such processes. Thank you very much.
Q&A session. We have not yet received any questions from the audience, so I would really appreciate it if you would put your questions in the chat at the top right of the screen. And the first question I'm going to offer out there is one that I came up with, which is how will digital twins support AI and ML? And I think we have a little bit of time to go into some detail if we need to.
Okay. Shall I start? Or
Yes.
I mean, I tried to illustrate that already a bit. We have this experience in metrology whenever we assess data analysis methods that often you start with, if you have a good model, you start with simulated data. So digital twin you could see as a model of the measurement process. And of course now artificial intelligence are quite complex data analysis methods. And so they depend on these training data that you put in. So it's a little less straightforward than in standard metrology, but having a digital twin which gives you data which are comparable to what you have in the measurements allows you to produce controlled reference test data sets. And I guess medical examples are complex, as I mentioned, but this has been done also in other fields. Coordinate metrology, that's quite well established, and I could probably put the ball to Alistair, because Alistair, you have been working in this area and there have been similar ideas, and it would be interesting to hear from you also if that is something that is furthered in direction of artificial intelligence methods or machine learning.
Yeah, okay, Marcus. So one of the big issues about artificial intelligence and machine learning is do you start purely with data, training data, in order to build up a model of a system that you're interested in? Or should you base the analysis of the data using a model of the system that you've already constructed based on physical theory and similarly? And so I think from my point of view, I think if you've got a whole physical model that you have a lot of trust in, then somehow you want your data analysis to take advantage of that model, so that it extracts more information from the data because it's already based on what physics we know of the system and so on. But I think the machine learning can supplement that model, because all digital twins to some extent will be approximate, and the data is there explaining to us from the real world what is actually going on. And if you can use machine learning, artificial intelligence to update our model, learn more about the physical system, and then that's the best of both worlds.
So in a sense, what you're suggesting is an iterative approach to try and kind of get away from the chicken and egg problem. You know, it's which do you start with? It's you've got to start with something, and then you augment it with the AI machine learning to be able to make it better over time as a model.
Right.
Yeah, so there's talks about calibrating computer models, for instance. And, you know, in some sense that we're using data to calibrate the model or augment the model.
I guess there's the principal problem, if I can add to that, that you usually don't have you have typically very detailed models, but you have from the computational side, in order to realize a digital twin, you have to constrain what you put in. And that leads to, as Alistair already said, optimization errors. And then this approach, either using machine learning or other data-driven models, help then to pin down the model and effectively reproduce data, which then, on the other hand, could also be used again as data sets which are very well characterized, good described, and so we know what to expect, and we can see then how machine learning will do on that as well. Yeah. Mm-hmm.
I could also add that the issue of explainability of machine learning is in part about, well, given the results of the machine learning, how can we absorb those results and update our models? If we've got no idea what the machine learning is doing, if it's just a black box, then it's giving no real insight into which parts of the models need to be changed.
Okay, you've given me a lot to think about here. Now, here's a very open-ended question that I came up with, which is, what is the most important issue relative to units and maybe metrology in a general sense that is needed for AI and machine learning? You know, that's obviously what the workshop is about units and supporting units as part of metrology. You know, what's the most important thing that we kind of need to solve initially to be able to go down the path of being able to really handle units as part of an AI or ML system?
I guess I can make a start at that. So one of the issues that, again, is that we may, as metrologists, and scientists in general, we might work very hard to make sure that the input data is represented correctly, and is traceable to units in the metrology sense. But then we are applying some software, and the software we employing software written in standard computing languages that knows nothing about units, knows nothing about physics, and the outputs of the system software could introduce scale factors so that any traceability you thought you had in the data is entirely missing from the outputs. And so that's an issue, and that's an issue with any piece of software, not just machine learning and artificial intelligence. So the issue there is, how do you, in some sense, assign traceability to the outputs? So one of the areas of research is how you make computation reflect units or embed units into the computation. And we can do that using computer languages that allow you to type variables according to whether a mass or a length, and you can embed the units into that system. So the computation always respects the units that have been input to the data, and can never assign a variable which represents to a mass equates that to a variable that represents a length, because the compiler would say this can't happen. So that's one area that we're quite interested in, is embedding the units and the traceability into the calculations.
Okay, yeah. I mean, again, obviously these days, machine learning has gone through quite a wild period in the last couple of years, and often when machine learners come to us as metrologists, they would say, well, do you have any reliable data? Because this is really what is hard to get off, because everyone who has them and uses them for his own research will not necessarily share it with all the world, or if it's commercial interest involved, that's usually basically the goal. And so it's then very hard to assess what algorithms are doing. So you can read reports of success rates. It's very hard to see how much the algorithm was doing and how much the data went into that. And so basically having units obviously is a way to give a framework which characterizes well the data sets. And the other issue, ideally, if you have statements on the uncertainty in the input to such algorithms, you could probably assess how good the input is. Because an algorithm may fail because it's not well devised, and then it shouldn't be used anymore, or you would say its quality is not fit for purpose. On the other hand, it may also fail because it has used inappropriate training data. And so I think that's a bit the survey that I introduced briefly in the beginning of my talk is a bit going in this direction. Metrology could probably put a framework and help to standardize state data sets, so that's really important to have reference data. You may think in the future of having something like a platform. The medical field I cited with, that's of course an older issue. How can you get an algorithm which can save the doctor's work and let you classify or diagnose this? And the way these algorithms are traditionally checked are if somebody has a good test database, and which is not made public because otherwise you can manipulate the algorithms. And so you send your algorithm there and they test it with this database. And that's something probably that will spread to many other fields also. So metrology, by setting some kind of formats for data sets and also making people sensitive to the issues of uncertainty, could probably help a bit in there. I don't say that the machine learning community isn't thinking in similar ways, but we are used to do that very systematically. So I guess that's certainly some fruitful area of interaction. Yeah.
Just a reminder to everybody, we're still taking questions, but there's one from Victoria.
Thanks, Stuart. So I really enjoyed your talk, and Marcus, your perspectives really resonated. It's interesting to note that metrology is not sure what AI can do for metrology, but we're sure that we can do something for AI. And a lot of that really hinges on these ideas around trustworthiness of data and reference data and confidence in data. And when we think about things like trust and confidence, they're very subjective, right? So who decides what is trusted data, and how do we kind of quantify that? And are we purely going to rely on traceability as being the driver for trustworthiness? I'd just be interested to.
Good. Alistair, you want to say something first?
Yeah, yes. So the metrology community would say that we've put in place all these measures to ensure traceability and trustworthiness. So for one thing, we've got an organizational structure that supports coming together and making decisions about what the SI is, for instance. We invest in a lot of experimental activity to make sure everything is working correctly in the form of key comparisons and so on. So there's a whole pile of strategies that we put in place to make sure that our data, that reference data that we produce, is trustworthy. But in industry, they would quite often take the view that trustworthiness is really about a statement of competence of the organizations, that with Rolls-Royce are competent to provide aerospace engines and so on. And how do you sort of quantify competence? It's a very human thing. And so I think one of the issues of how competent is a machine learning algorithm, how competent is this AI system, that's a lot softer, and I think it's a lot more difficult to quantify that, and it's one of the issues that we're struggling with.
Yeah, I would also say that in the end, what we discuss a lot in metrology institutes and also in the larger organizations is that there should be something like a quality infrastructure, because that's usually what people look for. I mean, if it's ISO, or if they would put their stamp on that means something. Is that's what Alistair meant when you say, okay, this is the competence of the organization. But actually, you said this. It seems metrologists tend to think more that they can do something for AI than vice versa. I think that's starting to change, because at least NPL for some years already, and PTB is stronger and stronger. The bigger institutes, they all see that impact, because also they affect lots of areas of metrology anyway in the future, because these algorithms will be used, if we may like it or not. So I guess basically we need also a collaboration between us and the machine learning community. So it's and they will, because otherwise they will just develop their own quality infrastructure, and but that's really where things will go in the past. And I think some metrology institutes would say that that's certainly a future important area. And I can tell you from what I've been observing in other European institutes, most prominently in NPL, and what we have in our place, it's really that's really a very intense ongoing discussions, and we need this link with the community to understand what they are doing, and they may benefit from us in the end, because we have a qualitative infrastructure for somewhat related problems, but not at that level. So really, it's something. This infrastructure has to be built in a way, and it's really a job for the future. And right now we do just the first steps. So I think would say we build competence in the NMIs, as well as, of course, in the outside scientific world. And Yeah, and then important is also these kind of examples where we can show how to go forward, and saying we have concepts for data and how to standardize them will help there certainly. So I think it's not an exhaustive answer, but it's yeah, it will be very interesting developments in the future that I expect to see.
So this has resonates with me a little bit. As an analytical chemist by training, I'm very familiar with things like standard reference materials, which are produced by NMIs, and they're physical things. Are we basically saying here, or at least that's what I think I'm hearing you say, is that maybe there needs to be digital standard reference materials for AI and machine learning? And the only problem with that is, in a sense, you could say that's, those would nominally be developed by the NMIs, and then they would be, I don't want to say eating their own dog food because that's a bad acronym, but that's a bad commentary. But in a sense, it's you'd have to have some separation, obviously, of that capability to then be able to put that out there as a way in which to be able to, standardize or work towards a standard for AI and machine learning algorithms that are out there in the community. Am I off base with that, or is that kind of sound like?
It's an interesting analogy to say these standard reference materials. I would say digital reference materials in the form of either digitalized measurement data, because that's what the machines need. I mean, Alistair described that quite well in his presentation. And then in addition, this issue of digital twins, which is also a capability that Metrology is just building, and will also require a lot of collaboration with experts, say, for modeling, data analysis, and machine learning, as we discussed earlier.
I think the machine learning community have, invested in producing standardized training data and classification problems and so on, so that the community can test the effectiveness of various algorithms. And so in some sense, there are starting to be those sort of digital reference data that can be used to assess the effectiveness of different algorithms. I think the issue about calibrating computer software and systems, is also that desire to put a stamp to say that this analysis method is fit for purpose. A standard operating procedure, a standard deep neural network set up in such a way will perform this task to effectively. I think that's the way that metrologists would tend to think about these sort of things. I have also a question about, we've talked quite a bit about how we make data fair so that analysis systems can access that data. But should we also be talking about, well, what about the output? How do we make the outputs fair and findable? How do we assign the provenance to the outputs so that the machine learning or any analysis system is putting the outputs back into the science community in a way that is fair? I don't know, Stuart, if you have any thoughts about that.
I don't know that I have many thoughts other than it would seem logical that needs to be done. And in fact, one of the questions I was kind of formulating was around, as was commented, the transparency around, how algorithms were run. So in a sense, it's not just the inputs and outputs. Maybe it's actually also the workflows for running those algorithms. And so in the fair context, preferably the inputs, the outputs, and those workflows would all be made available for people to evaluate in a way where they could nominally run that same analysis either on an equivalent system running at their institution, or on quote equivalent data to see if they got something that was the same or at least equivalent in however that was termed. So. when you start thinking about fair, it very quickly makes you realize that you kind of have to be fair everywhere. And that's easier to do in some situations and certainly harder to do in others. And so, you know, coming to that realization is a really good thing for, I think, this process, this workshop as the start of, you know, this effort, because, you know, if that's built into the whole idea about how things are done, then hopefully the outputs of this whole process will end up being exactly what we hope they will be, which is fair and evaluated in a sense generally by the community, so that you know, it's not like this group over here can do it and do it right, but nobody else can. We need to make sure that whatever is done is, you know, is put out there for others to critique and to evaluate.
Yeah, that's a really important point. And it's important to get that collaboration between all of us going on that. And I guess that's why events like this are so important. Just conscious of time, we've got about 4 minutes left, so it's probably a good point just to ask for some final perspectives from Marcus and Alistair on, you know, where we're at and key next steps that might sort of start taking us forward as a cohort in this, with some of these questions.
Well, yeah, so if I could start with that, I think one of the maybe 3 issues I would say has come out of this discussion would be, for one, that the metrology community and the machine learning community, or more generally the scientists and the machine learning community, have to get together to solve this problem. There's no way that the solution resides within the metrology community. You know, so we need to talk to the machine learning AI community to see how we can work together on this. I think the second point is the point that Stuart just made, is the fact that when you start to think about things from a fair point of view and make it fair everywhere, then all of a sudden, you know, you start to question whether or not, you know, our working practices are as good as they should be. So I think that's quite important. And I can't remember what the third point was.
Well, maybe I can add one, Alistair. So yeah, I think also what we have been talking about, and Stuart's last comment went in this direction, that I think all of this needs. I mean, it's not only artificial intelligence and machine learning, but science in general needs strong improvement in research data management. And I would say what this workshop does is actually putting one important backbone into it to reflect on physical data, or fair principles Alistair mentioned. But fair principles are, of course, not only in our community a big issue, but it's really in the general scientific community. And in Germany, for example, in parallel, and also here, we as metrologists engage quite a bit. We have this initiative to build up something like a research data platform on the national level, and then we have in all kinds of scientific publications outlets. There's more and more demand, and I think that's very important also, that data are made accessible. The outputs have to be made accessible in a reasonable form, and maybe used then in other works, or maybe used as input for quality assessment or whatever. But I think that is very closely related, and should also be kept in mind. So that in a way takes up more the point Alistair made. It's really something that needs a lot of interaction between us and the wider general scientific community. So we are one player, maybe not the biggest in that, but it's really some areas where we can give specific good input there. And on the other hand, to further metrology, we will also need these things which come from the outside, the machine learning expertise for the AI topic, obviously, the practice they have developed there, but the research data management also will have to go to another level, because we will go away really from having these small, very valuable data sets done with high precisions, which still is important and will still be referenced in the future, but we will expand there a bit to areas where you have to deal with bigger data sets. Yes. I hope that was the third point, Alistair.
Yeah, that was a lovely summary, and I think unfortunately we're going to have to leave it there for this discussion. And so I'd like to thank you both, Alistair and Marcus, for your inputs and your time today, and also thank you, Stuart, for valiant moderating. And to anyone who's out there in audience land, thanks for listening in, and you now have a 10-minute break in which you can change rooms, and hope it's been useful for you. Thank you.
Thank you very much, Sue.
Yep.
My name is Victoria Coleman. I'm the chair of this session. I'm located at NMI Australia in Sydney, and I'm currently the APMP lead technical chair. And I'm joined by Stuart Chalk, who's the moderator of this session, and I'll just pass over to Stuart to talk about how Q&A will work.
Thanks, Victoria. As we go through the presentations, you can put your questions in the chat at the top right here. And when I get those questions, I'll make them available so that you guys can upvote them with the thumbs up symbol there. So please submit your questions, and we need a lot of questions because we've got a lot of time at the end for discussion.
Thanks, Stuart. So we've got about 45 minutes all up for this session. We've got two talks. The first from Alistair Forbes, who's going to introduce the topic for us. Alistair is a fellow in the data science department at MPL in the UK. And the second talk, which is on reference data for trustworthy machine learning and metrology, is given by Marcus Barr from PTB. And Marcus is the head of Department of Mathematical Modelling and Data Analysis at PTB, based in Berlin. So please do send through those questions, and then after we've played through the recordings, we'll meet back for about 25 minutes of panel discussion. And the more questions we have, the better that discussion can be. So with that, I'll leave it to our host to set on the recordings, and see you soon.
Hello, I am Alistair Forbes, a mathematician working in the data science department at the National Physical Laboratory, the UK's National Metrology Institute. I want to say a few words about this discussion session in the context of the SI Digital Framework Initiative. The SI provides a basis for the international measurement system. The aim of the SI Digital Framework is that all aspects of this measurement system, measurement results, uncertainties, traceability, calibration, and so on, can be accessed and interpreted digitally, enabling machine-to-machine communication, enabling the analysis of data by computer systems, for example, statistical analysis, finite element analysis, computational physics and computational chemistry calculations, and also the analysis by artificial intelligence and machine learning systems. The framework envisages three layers: the core layer, a service layer, and an applications layer. The SI core layer is concerned with the basic elements of measurement, representing measurement results in terms of a numerical value, associated unit, and uncertainty. The service layer is concerned with the wider services and products provided by the National Metrology Institutes and similar organizations that directly support the integrity and traceability of the measurement system. The applications layer is concerned with tools and services developed and deployed in the broader scientific and technical community, and includes analysis and artificial intelligence and machine learning methods. This discussion session primarily relates to the applications layer. The FAIR principles feature strongly in this workshop. These principles are aimed at improving the findability, accessibility, and reuse of data, particularly by computer systems operating with little or no human intervention. The FAIR principles are there to help machines perform tasks that are useful for us. While the immediate aim of the SI digital framework is to provide machine-readable data, this longer-term aim is to provide machine-actionable data. The data should enable interpretation, analysis, reasoning, and decision-making by computer systems, again, operating without human intervention. And for this to happen, the computer systems must, in some sense, understand the meaning of the data. So the correct interpretation of data will generally require an appropriate knowledge, representation, and reasoning framework, employing controlled vocabularies, taxonomies, ontologies, and the like, and inference tools based on logic and statistical inference, for example. There are many issues that you may want to discuss in this session. One topic of interest is how can we ingest data and metadata into analysis systems? So we want to make sure that technical data is represented correctly. But we must also be concerned with the FAIR principles. In particular, the data must specify what individual or system it relates to, what physical artifact, what individual, which chemical compound, material, and so on. And this is really what findability and FAIR is about. A second topic is how we assure and assess the trustworthiness of the outputs of analysis systems. A fundamental aim of metrology is to ensure that measurement data used in analysis is trustworthy. But we're also concerned with the trustworthiness of the outputs, not just the input data. And this presents a particular challenge when the outputs depend on training data, depends on models, depends on algorithms and software. So a related topic is how can we encode the provenance of models and algorithms and software in workflows. We may be able to specify the provenance of the data, but how do we specify or encode the provenance of the model, algorithm, and software underlying the analysis? I hope you enjoy the discussion session. I now pass you back to the chair of the session.
I will talk about the potential role of reference data for trustworthy machine learning and artificial intelligence algorithms, taking a metrological viewpoint. In the first part of the talk, the relation between machine learning and metrology is discussed, and in the second part, I will present a use case stemming from a European project in a medical physics application, and finally, I hope that this will give some ideas what could be potential paths towards standardization. For the role of machine learning and metrology, I can cite results from an artificial intelligence survey conducted among 14 European NMIs in the framework of the European network MASMET, which is a part of Euramet. And here this relation was considered from two different angles. So one viewpoint was, are there things metrology can contribute to artificial intelligence? Can it improve these methods? And the other direction was, in what sense do these new algorithms are extending the capabilities of metrology? And on the first item, obviously, classical quality infrastructure aspects such as uncertainty, traceability were mentioned. Robustness, explainability are other things which you would like to have for a solid metrological assessment of artificial intelligence results. On the other hand, of course, there's many computationally intensive metrology applications where artificial intelligence algorithms may be beneficial or enabling. I listed some typical tasks which are often difficult to solve, and in particular here new applications of distributed measurement systems such as sensor networks or in general systems which produce a lot of data are potential beneficiaries. Okay, So from the results of the survey, there were less answers for the potential of AI for metrology, but certainly handling of big data is in the bigger NMIs an issue. Again, sensor networks, distributed systems feature highly, and it was also sometimes said that systems metrology is an emerging field. So there will be more and more systems where large number of measurements are combined. Another area, of course, highly resolved imaging and microscopic processes where a lot of pixels are produced. More answers came in the direction of how metrology can support for artificial intelligence. A potential connection was in particular seen in transferring ideas on uncertainty and traceability. And there, obviously, one main issue is how the input of measurement uncertainties affects the outcome of artificial algorithms and what procedures enable this determination. And the second most cited application there was reference databases, and that's actually the topic of my talk. And that could be measurements, but I will also have an example in a minute on simulation data. The general issue is, of course, data quality is a possible basic way to assess the suitability of a reference database. And all of this feeds into standardization, obviously. For future research priorities, consequently, trustworthiness, security, and contributing to quality infrastructure was mostly cited. The training data quality featured high in the column on reliability, which in general seemed to be the most important concern for metrology institutes. I will not say much on explainability today, but certainly traceability with its uncertainty issue is a main concern, and examples in metrology should be identified and are important to put this area forward. So I will give you an example which comes from a project in the European Metrology research program, EMPIA, and that is metrology for electrocardiographic automated data analysis. It's running a project called Medalcare. We reached halftime now, and the two main objectives is, first of all, to assess metrology for advanced data analysis, including machine learning. And the second part is to provide reference data for these artificial intelligence, actually to enable such benchmarks. And here we started from a clinical ECG database, which is called PDB-XL. And the goal of the project is nevertheless to extend that and to provide a data base made out of synthetic data with a ground truth. And that means they will be generated by established biophysical models. And there you would know exactly what you put into the simulation, what kind of pathology is implemented in the model, and how it affects the ECGs. And obviously, hopefully, if this all is successful, it will further clinical applications and standardization in this important practical point. So a reference database of measured clinical reference data is PDB-XL. It has 20,000 ECG recordings of 10 seconds duration, and in each of these records are 12 leads measured. And for each of the recordings, we have a diagnostic and rhythm statement from two experienced cardiologists who use the well-known ISO standard classification, and that leads to separation of the whole database in superclasses. So about half of the ECGs were from healthy, normal people. Then there's different pathologies, and each of these pathologies goes again into subclasses. This was done in collaboration with the Fraunhofer Heinrich Hertz Institute and is published in Scientific Data. Now, with this database being available, there was a first benchmark carried out for different types of machine learning algorithms and also some conventional signal processing algorithms such as wavelets. You can see the results. In general, it was found that machine learning is superior with high success rate at above 90% compared to all conventional previously used algorithms, especially ones who extract features, which is often what software in the practical doctor's practice will do. And then also first steps were done towards explainability. As I said, this is not the main feature, but you can use this information also to identify the parts of a 12-lead ECG record which have most influenced the classification in one particular illness class. Again, this is also just published by our Fraunhofer colleagues in collaboration with PTB. But the main point of the project was its new aspect, implementing a modeling pipeline. And here that requires modeling of the ventricles and the atria of the heart. Here the ventricle part is shown. So you define mathematical equations and you run them. And first it's done on the isolated surface of the heart where you can make catheter measurements and validate these models so that all has been worked out already. And then in a second step, to get the ECGs, you have to embed them into torsos. And here we have a cohort of 13 models taken from direct medical imaging recordings, different hearts embedded in different torsos, obviously, and the black dots in each of the pictures are the points where the ECGs are taken. Okay, and if all of this is put together, you can simulate ECGs for each of these people. You can also put pathologies in the cardiac dynamics, which are often mechanistically known, and then you get the resulting ECG here plotted in a typical version that doctors are familiar with. And you can also superpose noise. So in other words, you can vary the quality of the data and then see how that may affect the machine learning algorithm. The main goal is actually to test such algorithms with well-defined data records. Okay, and that brings me already to the summary. In short, I discussed a bit the issues that metrologists found important in trustworthy machine learning. Main conclusion is, of course, training data are key. And in particular, we have a lack of quite high quality references. So we should work to set up reference databases and also find criteria to assess these databases. And that would be measurement data. But another second path, which is very promising, is to use synthetic reference from digital twins. The medical example I showed is already very complex with respect to the processes and equation setup, but obviously this can be beneficial probably in simpler, better understood physical processes. And hopefully if these things can be established, they can be an important element in the standardization rules for such processes. Thank you very much.
Okay, well, it looks like we've got some questions from the audience. So let me go ahead and start with the first question for our speakers. Does the QI infrastructure need adaptation to incorporate FAIR principles for big data, AI, and ML? Whoever would like to take that first.
Okay, I think the QI infrastructure certainly needs to think about computation and how it fits into the quality infrastructure. So the infrastructure currently is very well placed to deal with issues, physical measurement and the like. But the question is about how it deals with computation and how we can qualify and calibrate computation. And that applies in particular to how we deal and assess the competence of AI algorithms and machine learning algorithms. So the quality infrastructure and this meeting is demonstrating that the quality infrastructure is aware that it needs to develop more methodologies and protocols to deal with computation. So I think we definitely recognize that we do need to adapt and extend our remit to take into account the computation, and the FAIR principles are part of that issue.
Yeah, very well put. I mean, the thing I could add is, of course, that having data available is something which is in particular important for artificial intelligence, machine learning. That's not always the case, and data are kept for various reasons, often within a narrow range. So having them accessible for a wider audience, and actually, especially in public funded research, it should be made a principle that the data which went into that are also then to be published and so on. And that will certainly help the development of the whole field. I mean, that's what my machine learning colleagues in the German environment tell me, that that's often what they don't have, and that's what they appreciate if metrology institutes have it. But yeah, that's that.
Okay, thank you for those answers. Let's go on to the next question. Are there things we can learn that can be applied from other data-intensive fields, such as astronomy?
Yeah, certainly a good point. I mean, I'm not an expert and I don't know exactly what astrophysicists are doing, but I can tell you, for example, that PTB has started to implement a research data management unit, and one of the key people there is an former astrophysicist. So certainly there is a development in both astrophysics and elementary particle physics, which are paving the way also, because metrology often doesn't have this huge amount of data. So I mean, I'm not sure how much of quality infrastructure perspective they will take, but they have developed practical ways, and that's important to interact with. Yeah.
Yeah, I would say definitely we need to learn from other communities. I think in some sense that the success of the metrology community is based on keeping things as simple as absolutely possible in order to provide the accuracies of measurement that we're able to attain in the laboratory. And one of the main things we do is just get rid of all environmental factors so that we do all the measurements in a controlled environment and are able to attain the accuracies. So and the link between the measurement result and produced by the instrument and the measure end is as simple as possible. But as soon as we start to think about our contributions to the wider science area, in particular environment, biology, medicine, so on, all of a sudden measurements are being done outside the laboratory and involve computation to get sensible answers. And then we need to think, well, okay, how do we make sure that we're still attaining that traceability, that trustworthiness, taking into account the fact that the measurements are being performed in a system where the environmental effects are not controlled. And I think, for instance, I think the life sciences have been one of the drivers of the FAIR principles, because they've recognized this need to work with data and attain interoperability, something that in metrology communities sometimes takes for granted because we're working to very controlled protocols, whereas in the life sciences, that's not possible. So I think definitely we can learn from many other fields, and indeed the astronomy community is one of those fields where by necessity they've got a very expensive resources, and they need to make the absolute best of those resources in order to extract the largest information gain from those resources.
So I have a follow-up question for that, which is, based on that comment that in a sense metrology is or has been a relatively controlled environment, but yet now we're talking about taking it out into a situation that's more real, in a sense, more real world outside of that controlled environment. Does that mean we are going to have to change a little bit the perspective of metrology in these more real world situations? Are there, I guess in a general sense, we're talking about other sources of uncertainty, and so maybe that's how it would be factored in the metrology sense. But I'm not an expert, so I would value your opinion on that.
I think one of the ways we've looked at this, in metrology, we talk about uncertainty evaluation and uncertainty budgets and so on. But more in the last 5 years, we started talking about uncertainty quantification, which is a more broader approach to evaluating uncertainty. And it's taking into account all the uncertainty contributions, which include not only the measurement uncertainty, but the uncertainties associated with the model, the uncertainty associated with computation, the uncertainty associated with the fact that we might not know exactly what we're talking about. There's a specification uncertainty and so on. So our uncertainty quantification tools are broadening to take into account the fact that we're trying to address issues that aren't solved by doing experiments in the laboratory. So I think we are looking to broaden that outlook. However, the metrology institutes, for instance, what is their core job? Well, is to make sure that the foundation is correct. So to make sure that the SI can be used effectively in science and technology. So I think the community as a whole has to address this. How much is due to how much the NMI can do and how much the NMI should be doing. That's part of this conversation.
Maybe let me add one aspect. In the first part of your comment, Stuart, you said that is metrology changing, or how would it have to change? And certainly, I think what we have been seeing over the last years is a stronger awareness to influence of models. Alistair already mentioned model uncertainty and these kind of points, and also to the algorithms we use. The more complex the data we deal with, the more algorithms play a role. But even in pushing metrologies to, say, nano limits or highly resolved things, we have already these things. So I think one way we are changing is to have more expertise in modeling data analysis, and that is some trend we see over the last 10-15 years. There's more people working in these fields, and that's important to deal with these more complex measurement issues. Yeah, so that's probably an important addition thing which is also necessary to link with the machine learning and then the communities we have been talking about. Yeah.
I had a point of reflection there in drawing actually on a previous discussion where last session we spent quite a bit of time talking about data trustworthiness, and it's really interesting to reflect on the fact that astronomy being a big data field where there's a lot of investment made and seems still quite self-contained versus something like healthcare where decisions really matter and you really draw on that necessity of trusted data, and that's when I guess the currency of what metrology can offer and that sort of that validation and that sense of trust really comes to the fore when you're making decisions about essentially life and death in some cases. So yeah, just interested to kind of tie that into your perspectives and yeah, basically get your take on that.
Yeah, so one of the things that I sometimes think machine learning, machine learning can be used for lots of things, but one of the things it can be used for is discovery, to find out correlations between data streams that we didn't know were there. And once that correlation has been established, then we can apply our science disciplines in order to understand why that is and extract information and learn new things. So I always used to say that machine learning and big data would have never have found the Higgs boson, for instance. You've got expensive pieces of equipment designed on scientific principles in order to find the Higgs boson and other things. But it turns out, they would have never found the Higgs boson without machine learning, because you needed machine learning and image analysis to find the interesting traces that allowed them to pinpoint the information that's interesting. Similarly in astronomy, where in order to find the interesting things, you need image analysis. So for discovery, it's machine learning has many benefits. But if you're using machine learning for quantitative decisions, then all of a sudden, you need that element of trustworthiness. You need to have that reproducibility. You need explainability. You need to be able to defend your decision in court, perhaps. And that's where the metrology mindset, in terms of sensitivity analysis, traceability, uncertainty, and things like that. That's where our thinking is maybe is useful.
Okay, well, I'm going to go on now to a question that I put in the chat. And this is a question that came out of actually a conversation I had with a metrologist that is at NIST in the United States. And he had emailed me and said, I'm still not yet convinced that metrology needs to be represented in an ontological context. Can you give me a reason or reasons why it should be? What is the need for it? And in my answer, what I came up with was this issue that metrology still has, which is the issue of units of dimension 1, where I said to him, if I as a chemist have a piece of data which is a mole fraction, which is the fraction by mole of one substance within a mixture of two substances, and I also have a piece of data that is about a mass fraction, which is the ratio of the mass of a substance divided by the mass of all the substances, I know that those two numbers are not interoperable with each other. I can't add those two together. They are different. Even though they're both dimensionless, they are different. They're based off of different units. And so as a consequence, I can't bring them together. And I have to do a calculation to be able to convert one to the other. How can we deal with this kind of situation when we're talking about AI and machine learning? How can these systems be able to distinguish the difference between units of dimension 1 when they are based off of ratios in particular?
Yeah, it's a very interesting question, and one that the metrology community have been discussing a lot, because it's it's a real issue. And I think part of the issue with artificial intelligence is that you have to encode, in order to employ software, you have to write it in a language, computer language, and that computer language is all that the machine knows. And so the nuances about different quantities that have dimension 1 are completely lost in the machine, unless we have some tools to say, okay, that allows the machine to understand the meaning of all of this. And I think in some sense that's what's driving the metrology to look at things like ontologies and taxonomies and knowledge representation, because we want machines to do a lot of work for us, but we want them to behave sensibly. And in order for them to behave sensibly, we've got to give them some idea, the meaning of the things that we're trying to do. I think. But this is difficult, and the computer scientists recognized this was difficult 50 years ago. That natural language processing that humans doing is very sophisticated, is very nuanced, compared with poor old machines can do, working with reals and integers and double precisions. So until we provide the machines with some way of capturing meaning, then they're always going to come up with answers that to us will never make sense. But to another machine will make perfect sense, and they'll go on and make decisions and do things that physically or from a chemical point of view just can't happen. But they'll be happy enough because nobody told them anything different.
Marcus, what's your take on this?
Yeah, I would basically agree, of course. I mean, again, going back to my more specific topic, that would be also the issue you want to have in these reference data, because I mean, the answer to your question what will the machine do if it has two units, two quantities which look the same but have different origin, and we can easily distinguish? It cannot do anything, and that is a big practical problem. I mean, I have a bit more to do with health metrology applications lately, and then there is also these issues. If you would just collect data from many different devices, it's already known that basically if you have a device from manufacturer A and B, that make a difference. So what, independent of what we do in metrology, also the whole health community tries to set up these national cohort studies, which are another way of giving reference data sets. So I guess that is that is an important issue, and if that's not solved, it will be always a bit difficult to assess, and then there is a big source of errors and wrong decisions to be made there. Yeah.
Interestingly, I can report that in a previous session that I was in this morning, there was a talk by Michael Trott of Wolfram Alpha, and their way of solving this problem was to just encode both the numerator and the denominator units and go from there. Now, I don't know if that's actually a solution, really, but there are at least, the community has come up with ways to try and deal with this, and so in a sense, I think the onus is on metrology to try and deal with this. And I know it's been a big topic for a large number of years because it's a very difficult topic. But in a sense, I wonder if this particular topic and maybe some others closely related need to almost be resolved before we can truly say that metrology can be represented in some kind of ontological way. Just because, what the issue, I think the issue that the scientist at NIST that was really trying to get at to me was, I'm not going to trust an ontology unless I know that it really truly accurately represents metrology. So maybe that's what needs to happen, I guess, in a sense.
It's certainly, Stuart. I would emphasize that point, and we've had some discussion at NPL just yesterday, I think it was, about are these ontologies that are being used in science and technology, do they really respect and add, do they reflect the SI as we want it to be interpreted exactly, or are there slight misrepresentation or ambiguities that have crept into these ontologies that really the metrology community need to help resolve?
I think it would be great if the metrology community would get more involved with the ontology community, and clearly that has to happen, obviously, because that's core fundamentally to the machine learning AI side of things. I'm taking some notes here. Okay, we have about 5 minutes left. We have one last question, which I'm going to throw out there, but I don't expect easy answers because it's about pain points. Are there obvious pain points you've come across in terms of implementing units for AI and machine learning? Maybe we've already touched on some, I guess.
Yeah, so it's all pain.
Just data, yeah.
but I think that one of the research areas that we're looking at the moment is computation that has units embedded in it, so the compiler knows exactly what to do with these units in the correct way. And again, going back to the previous point, there can be solutions that look as though they're the right thing, but in fact might not be what we want. So having general computation that reflects units, would be a step in the right direction. Similarly, having data that comes with the units embedded in them, so that one of the issues with a spreadsheet, the metadata is what's on the top of the column and the leftmost row. That's the metadata. But if you can extract this data in a cell and put it somewhere else, and it's no idea where it came from. We want to make sure that the data always takes its unit and metadata with it, so that that information is never lost. And the computer languages are capable of doing those sort of things. And so how we embed that sort of metadata into computation, so that machine learning or standard finite element analysis is already sort of unit enabled and unit respecting. I think that's an interesting area for science.
I should say it's there so far. For us, it has been relatively easy because we started with examples from metrology where we had some insight and control of the data, but certainly I expect also quite a bit of pain to come. I mean, seeing the plans and then what should be done in the next years, and the more we get into trying to influence or put a quality infrastructure for real world data, the more pain will come. Yeah. So far it has been not so bad, but we are at the start, I should admit.
Yeah. Maybe that's kind of, I guess, a good point to wrap up on for today. I mean, we're kind of coming to the end of our time anyway. So I guess I'd just like to take this opportunity to thank the panel, to thank Alistair and Marcus and Stuart, for who it's both either very early or very late. I really appreciate you taking the time to dial in for this not so friendly for you time zone. And I've really appreciated the discussions today. They've actually been, I've learned a lot, and I've definitely got some takeaway points to think about and to share. So with that, I guess we can call this panel closed. And I think there might be one or two housekeeping things to follow up on, but yeah, just like to extend my thanks to the three of you for your time today and your support.
Yeah. Thank you.
Thank you very much.
No problem.
Okay, so that kind of brings us to the end of the day today. We had very interesting chats in topic 4 across these 2 discussions, where we heard, amongst other things, the importance not only in FAIR principles in our data inputs, but also in ensuring that our data outputs follow FAIR principles. And I guess that's still a bit of a work in progress for the community. I think one of the other interesting takeaways for me was the point that we just heard in the last session about quality infrastructure and the need, or the recognised need, that we may need to do some adaptation and extension there to ensure that the sort of the methodologies and protocols for computation are incorporated. But I think one of the overarching messages, both from this session but from earlier in the last week or 2, was really the importance of coming together on this between not just the metrology community, but also scientists, data scientists, the machine learning and AI community, and also the ontology community. And I've definitely learned something from that point, because I didn't know that there was an ontology community before this week. So it's been really useful. So that's my short summary for today. I don't know, Stuart, if you had any other comments that you wanted to add, or any other takes.
No, I'm good, thanks.
All right, well, so that kind of wraps up this session for day 4, and just a reminder, of course, that tomorrow this session will run again at another time zone later on today. So that is at 1 p.m. UTC. And then tomorrow, day 5, we'll have a closing plenary around 3 p.m. UTC as well. So hope to see you there for that. And otherwise, thank you for joining in.
Thanks a lot.